So what I understood my role today is to give you introduction to permafrost 101. Right? And I will start with definition. So definitions. I will not give you too many, just very necessary ones. Well, first of all, permafrost. So permafrost, the most common definition based on temperature. So it's any earth material at or below 0 degrees Celsius for 2 or more consecutive years. That's permafrost. So pretty much material which is frozen for more than 2 years. And here on this slide is distribution of permafrost in the Northern Hemisphere. And you can see, without some details, most of permafrost is in high latitudes. And also in high elevations, like in Tibet Plateau. So it means that permafrost is a product of cold climates. And as a product of cold climates, of course, permafrost is very sensitive to climate and climate change. So one more thing I will use, one more term I will use is active layer. So active layer is the layer above permafrost. It's not part of permafrost, it is above permafrost, which is thaws and freezes every year. So it's not permafrost because it's not frozen for 2 more years, but at least part of the year it's frozen, and part of the year it's not frozen. Now, just a few numbers. So permafrost thickness changes from almost none in the discontinuous permafrost regions in the southern kind of part of distribution to more than 1,500 meters in Siberia. And active layer is usually between 30 centimeters and maybe 1.5 meters typically. In some places deeper, but typically this is the numbers. All right, so like I said, permafrost is sensitive to climate. And recent changes in climate, which showed in this slide, it's a warming in a kind of global scale for the last about 60 years, warming. You see that there is a substantial warming happening in the high latitudes, both northern and southern. And this increase in temperatures for this period of time now accounted more than 2 degrees Celsius, even more. And they're about 2 or maybe 3 times larger increase than in lower latitudes, in the center. Okay. Here. Yeah, in the lower latitudes. So there's lots of changes in climate, and this so-called polar amplification, of course, impact permafrost. And permafrost react. So this is a figure from a recently published paper with many co-authors from this network of permafrost, global network of permafrost, which shows here, this is the changes in permafrost during the just last couple decades on degrees Celsius per decade indication. And you see that pretty much all dots in northern hemisphere as well as in southern hemisphere, in Antarctica, they all orange or red. And temperature increase and higher latitudes also much more in permafrost, also much more substantial. Substantial because of increase in temperature is larger, and also because of properties of permafrost as such as well. So, and this increase is really huge. Like in Alaska where I work, in the North Slope of Alaska, all these dots, red and orange, at some locations temperature increased by more than 3 degrees Celsius for the last 30 years at 20-meter depth. So increase it's very significant. But then you say, well, how about thawing of permafrost and what we should expect in terms of not just increase in temperatures, but how permafrost, if permafrost is thawing, first of all, and then how it will happen in the future. Well, for that, I will step back a little bit and give you some a little bit larger perspective, time perspective information about permafrost. So permafrost, of course, could be in some regions very old. And it could be more than 1 million years old. But for our reason of our discussion today, probably the last glacial interglacial cycle here will be enough. So most of permafrost, which is now in danger of thawing, is or result of previous glacial period, or result of cooling after climatic optimum about 10,000 years ago, or very, very recent cooling during the Little Ice Age. So it's very schematic. It's very schematic. So we can talk about age of permafrost in our interest just like three categories: old, this last glaciation, kind of intermediate, last 10,000 years, and very recent, this Little Ice Age, only a few hundred years old. Now, how the permafrost was reacting to these big changes in climate, I would like to illustrate on this example. It's Eurasian kind of map of paleo permafrost distribution. And this figure shows that the maximum extent of permafrost about 18,000 years ago. And after this last glacial period ended and transitioned to climate transition into the recent relatively warm period of Holocene, permafrost was degraded. But it's important what it was there, what kind of permafrost it was that ancient permafrost is. So important to notice that it was very, very specific conditions, actually pretty not common at all recently. It's all all this mammoth steppe area, which was very, very widely spread during that period of time, pretty much disappeared by now. There's maybe very, very few very local exceptions for that. So what's that conditions? So tree-less environment, lots of wind, very cold temperatures, like 10, 15 degrees Celsius colder than it is right now, and very rapid deposition of kind of dust material. So at the same time, it was time of very developed fauna. So with lots of big grazers like mammoth and horses and bisons, and also predators there. So it means that even if it was cold, it was very productive environment. There was lots of grass, enough to feed a number of these big animals there. And with these specific conditions, what happened that, there's just example of one of the remnants. This permafrost layer, which we called Yedoma, or Yedoma, formed in a big, big area. And what is the specific of these sediments? It's about, some places 20, some places to 40 meters thick, and it's lots of ice in it, lots of ice. And this is example of this cliff. It's about 30 meters cliff. And white is ice, and dark is frozen material in it. And the frozen material contained also lots of organic material, because the sedimentation was fast. All remnants of vegetation and animals were buried in permafrost very quickly and still stay there up to now if this Yedoma is still intact. So the question is if it's thawing or when it will start thaw. That's a question I will try to answer a little bit later. Just a few other pictures from the same type of sediment. So this is person for the scale. And you see that this is in Siberia. It's in the Bolshoy Lyakhovsky Island. So this is ocean there. And degradation of permafrost here is in the form of coastal erosion, produce lots of this material which is slumping down the slope from this very icy material. So now, by the Holocene optimum, about 9 to 5,000 years ago, most of permafrost disappeared from European part and from Europe. Also, permafrost also melting now, or thawing, sorry, at the shelves because of inundation, because of sea level rise. It's still there, but it's thawing slowly. and permafrost regions shrink a lot. Now, after Holocene optimum, climate got a little bit cooler again. And for the last 5,000 to 6,000 years, it was generally, permafrost was generally, new permafrost was generally formed. So new permafrost in blue showed here brought us to pretty much to the present day distribution of permafrost, in this case in Eurasia. Similar environmental reconstruction could be done for North America. And a little bit more about Little Ice Age. So during the Little Ice Age, even younger permafrost formed. Because and it's usually formed in a very specific location, somewhere in the southern, near to the southern boundary of permafrost. And usually thickness of this layer is much less, about 20 to 30 meters. Why it's important? Because now I would like to talk about degradation of permafrost. So, well, it's pretty much common sense, I would say, that what permafrost is thawing first is, of course, the youngest one, because it was just product of very recent cooling. Now we are getting out of this cooling and actually exceeding it, and probably we're very close in terms of climate to Holocene optimum right now. So it means that conditions where Little Ice Age permafrost was formed, they disappeared, and permafrost is thawing. So young Little Ice Age permafrost is actively thawing. Just as an example, I brought here is this tunnel flats near to Fairbanks, south from Fairbanks. So there's some type of ecotypes with black spruce. They're intact. The permafrost is still stable there. But in birch forest and some others, say, permafrost formed only during the Little Ice Age. And by now, it's or completely disappeared or is thawing right now pretty rapidly. So that's what is happening right now. The Little Ice Age permafrost is disappearing. Now, what about late Holocene permafrost? Well, it was stable for a while, but now we actually get to the point that these permafrosts also start to thaw around Fairbanks, around interior Alaska, in Siberia. So this late Holocene permafrost is also started to thaw. So now how this process is going on, it's just very widespread, slow thawing, lowering boundary of the top of permafrost. In the warmer conditions, this lowering of the boundary develop layer which never freezes. So that's already another very important threshold. So we have in, say, interior Alaska, we have in many locations now some situation where layer, say, between 1 meter and 50 centimeters below the ground is not freezing during the winter. It's all not frozen whole year round, with all possibility to all processes going on, including biogeochemical processes. In a colder climate, this increase in summer thaw didn't bring this yet, but it will eventually. But not yet, not yet. What is happening there, which is important to know probably for you, how permafrost is degrading right now in a widespread area in the colder permafrost. Well, it's gradually getting some part of permafrost into the active layer. So that's what's happening right now. So just a very, very upper part of permafrost getting involved into the active layer, which freezes completely during the winter. But it's so in summer again, and it's summer thaw getting deeper and deeper, and a little bit more and more permafrost getting involved in this seasonal freezing and thawing process. So there is not a layer which is not freezing at all yet there, but it is coming. And I'm talking about just few tenths of centimeters. So it's very kind of slow, and it seems like insignificant even process, but if you think about it as widespread in terms of volume of the material, it could be substantial. Even if it's 10 or 20 centimeters, And every year we can gain like 5 or 10 centimeters. And the process is very tedious. Cold winter can freeze again, and then it's not linear. But if you think about longer-term process, you can think about it as a steady increase in this freeze-thaw layer depth. Now, this is kind of common thing what normal geophysicists like me will think about permafrost degradation. But there's other thing, so-called abrupt permafrost thaw. And it's a little bit different, because this happened, and it's happening already, and it's happening for a long period of time. In this case, the process doesn't care about age of permafrost. It's more care about the processes on the surface. Like in this particular case, this is North Slope of Alaska. Permafrost is still stable. However, there are some conditions, climatic conditions and weather conditions happen that some permafrost thawed deeper enough to get into ice, into very massive ice, and ice is melting, developing this subsidence. Subsidence fills with water, process accelerates itself, and we have something which cutting through all this. We just build it like first it will be Ice Age permafrost, then it will be late Pleistocene, late Holocene, and then maybe late Pleistocene will join the process. Well, in these locations, they're still local, they're still very limited in space, but in these locations, permafrost thaws through all ages, including this old Pleistocene permafrost Yedoma. And I can give you several examples of this, what could trigger it. And in previous case, it was actually weather conditions. There was some snow and then warm, melt of snow, rain, lots of precipitation immediately, and they developed this erosional kind of type of subsidence, and then it was increasing in the size and depth and so. Forest fire can also develop the thawing permafrost even in relatively cold conditions. So that's another one. Any actually other disturbances can trigger thawing permafrost and abrupt change in permafrost, developing lakes. And number of thermokarst lake, which we know in cold permafrost and in the warm permafrost, they exist, and they exist since already 5,000, 6,000, 7,000 years. And processes of thawing permafrost going on the bottom of these lakes. So permafrost is degrading under the lakes. So that's another example which nature don't care about how old permafrost is. The surface conditions will actually destroy even old permafrost. Now, just more example of this process, how it looks like. This is Fairbanks area, very recent developments there. And in this case, permafrost is thawing quickly. Also, the thawing of permafrost relates to lots of mass movement, very often to the aquatic environment, and the river banks, coastal erosion. It's all this process which we call it abrupt permafrost thaw is going on right now and accelerating. So we have more and more and more of these locations. So even if it's still very limited in space, the process is already going on. And if somebody would like to go and check what is coming out of it, you have a chance. You don't have to wait another 50 years when this old permafrost will start to thaw. You just go there where this old permafrost is degrading right now very quickly, and see if something coming out of it of your interest or not. All right, let's see. What else? Yeah, that's another just pretty pictures. Yeah. And why it's happening so quickly? Because there is so much ice there, and when it's exposed to the sun, to the atmosphere, it melts very, very quickly, much faster than it will take to go from the top down process. So it's very, very fast, very fast process. So that's also from Alaska and people for scale. So just very short what we should expect in the future. There is, of course, lots of modeling going on, and I could talk another 40 minutes or maybe half an hour, maybe 1 hour and a half. Well, I started later, so I think, within my 20 minutes. So very short. With projected warming, even with some relatively moderate warming, like say RCP 4.5, we will expect thawing of permafrost. This is present day distribution of permafrost by the mid-century. This is for, again, not for 8.5. This is 4.5 type predictions of climate change. And even with these predictions, so all this, of course, late Holocene permafrost will be thawing, and even part of the previous glaciation permafrost will be thawing. And by the end of the century, more than half, actually about 60% of permafrost will be thawing. And if you look at the locations where we know this kind of conditions exist, with very thick ice, very big masses of ice, lots of organic material there, they pretty much in an area where this thaw will actually penetrate into it. And lots of these sites will be rapidly, just falling apart, pretty much. That's what you will see from the surface. And what will be in the future, well, hard to say, but if we'll apply less kind of optimistic scenario, like 8.5 scenario as usual, even on the North Slope of Alaska, about 3/4 of North Slope of Alaska by the end of the century will be thawing, permafrost will be thawing. So actually it could be much worse. Thank you very much. We have a site you can get much more information, and thank you again.